Hey guys, today we will continue in our series where we go through the courses in FPGA Academy. Today we will continue with Lab 3. If you haven't watched the previous parts, you can watch them on my YouTube channel. I have also uploaded a Verilog practice where you can go through the exercises in HDL bits with me and I will explain how to solve them. So today we will continue with Lab 3 and we will look at part 3. We will look at Master-Slave D flip-flop. So Master-Slave D flip-flop has this circuit, and we can look at how this circuit works. There are two D latches, and we can have positive Master-Slave D flip-flop or negative. Positive means that the clock to the master is negated, there is a NOT gate, and if the slave clock is negated, if there is NOT gate in front of the slave, then it's called negative. And what does it mean is that when we look at this diagram here on the right, we can see that we have our D input here, then we have our QM, which is the output from the master, and we have QS, which is the output from the slave, and then clock. And if it's positive master-slave, that means that the QS changes on the rising edge. If it's negative, that means that the QS changes on the falling edge. So we can go through this diagram. So input D goes from 0 to 1, and QM on the when the clock is 0, because it's negated, changes to 1, and the output changes when the clock is 1. So immediately when the clock changes to 1, the QS output of the slave also changes to 1. So in this way we can change the final output Q, which is QS, the Q out from the slave. We can change this on the rising edge, and if it was negative, then it would be changing on the falling edge. So this is how Master-Slave D flip-flop works, and now we will try to implement it in Quartz. Create a new project, generate a VHDL file that initiates 2 copies of your gated D latch module from part 2 to implement the Master-Slave flip-flop. So we will first, we have our part 1 and part 2 from previous videos, and what we will do is we will create D latch. So let's create a new VHDL file, and we will copy our code from part 2 and we will save it as D latch. Okay. So this is gonna be D latch, and it will have, so we are now creating these 2 blocks, and these blocks have D as input and clock as input, and Q negative. And we basically don't need Q negative, or do we? I don't think we do, so we will just output Q. So we will have D and clock as inputs. It will be STD logic. And then we will have Q as output, and it will also be STD logic. Then here we don't need the attribute keep anymore. And we also don't need these, because the way we will do it now is we will use process as shown here. So this is a behavioral style of VHDL code that specifies gated D latch. So we will try to implement this now. So we have process that changes when D or clock changes. And then we have begin. If clock is 1, then Q is assigned D, and then we have end, if, and end process. So let's do that now. Process changes when D or clock changes. Begin, and if clock is equal to 1, then and if and end process. Here Q will be assigned to D. Yes. Okay, so this is gonna be our D latch, and now we can create new VHDL file for part 3. Let's call this part 3, and part 3 will actually have as inputs switches and as outputs LEDs. Let's save this as part 3. And we will import our component dlatch. So like this. And now we will initiate two dlatch components. One is gonna be master. It's gonna be dlatch port map, and another one that's gonna be our slave. And we can look at the wires. So our master will have D as input and negative clock for the clock. So it will have and we have to also look at, so switch 0 will be D and switch 1 will be clock. So in this case we have D, so switch 0 and switch 1, and we will say not switch 1. And our slave will have, we also have output, so let's create a signal. Signal Q master of std logic, and the input to the, this is not, yeah, this is slave. So the input to the slave will be our Q master, and the clock will be just switch 1. So Q master switch 1, and output will be shown on LEDR, and it's gonna be LEDR 0. Let's try to compile. Include the required pin assignments. That's done. Use the technological viewer to examine the D flip-flop circuit and use simulation to verify its correct operation. Okay. And component. And we will do functional simulation to see if it's correct. So this is gonna be a positive, since we have the clock for master is negated. It's gonna be a positive master-slave D flip-flop. Let's look at technological map viewer. So we can see our master has two inputs, and Q is outputted to the slave. The clock here goes to master and to slave, and then the output is shown here. So that's exactly as shown here. Maybe we can also look at RTL viewer. Yeah. So, and now we can do functional simulation, but I think it's not necessary in this case. I think this is going to be correct. So let's try to run it on our board. So program. So now our LEDR is turned on. So Q is turned on, and it should only change on rising edge of switch 1. So if I turn the switch 1 to 1, it turned off, and now it will turn on. And if I turn now the switch 0, if I turn D to 0 and I go down, it should stay as 1. Because on the falling edge, it doesn't change. But on the rising edge, it changes. So this is correct behavior. It works correctly. On rising edge, changes. On the falling edge, doesn't change. Rising edge changes. So we have finished part 3, and let's look at part 4. And in part 4, we will create three blocks. First one will be gated D-latch. So that's just one of these blocks, D-latch. Next will be positive edge trigger D flip-flop. So that's what we have created here. And the final one will be negative edge trigger D flip-flop. So that's this one. So that's gonna be the same as this, but the NOT gate will be in the slave clock, on the slave clock, not here. And then we will try to simulate it in Questa. So let's do that now. I have my part 4 here, and I will copy this from part 3, and we will create positive DFF, positive trigger D flip-flop. It will have as input D and clock. It's gonna be just STD logic. As output Q, also STD logic. And here, D latch, this is gonna be just D. This is gonna be not clock. And here clock. And output will be Q. We have our signal here. And we will save it here as positive trig DFF. Then we will create one more. This one is gonna be called negative. And the difference is the NOT in front of the clock will be here. Let's save this as negative DFF. And let's go to part 4. I will copy this component. So positive DFF, negative DFF. And our part 4 will have clock. It will have D and clock as inputs and QA, QB, and QC as outputs. And it will be the outputs of the D latch, positive edge triggered D flip-flop, and negative triggered D flip-flop. We have our components, and now we have to initiate all of them. So let's D latch inst. It's gonna be D latch port map, import map, and input will be D, then clock, and output will be QA. More. Here we create positive DFF and negative DFF. And this is going to be QB and QC. Positive, negative, and D latch. Yes, this looks okay. And now we just assign, and we don't even have to do this. So we have finished part 4, I think. Let's set it as top level entity and try to compile it if there is any errors. This is our positive. Negative DFF is not here. We have typo. Positive, negative, and yeah, looks good. So we have designed this, and now we don't need to use keep. Yeah, we have got rid of that. Compile your code, use technological map viewer to examine the implement circuit, verify that the latch uses only one lookup table, and that the flip-flops are implemented using flip-flops provided in the target FPGA. Okay. And use model sim, we will use Questa instead. Okay, let's see. This is done. Let's look at RTL viewer. No. So we can see we have 4 of these here. I will get this. So we can look at our you can see we have 3 instances. And here let's see what we can. Yeah, I'm not sure what we can see here. Yeah. Well, we have our 4 instances. What else? Technological map viewer. So let's open that. We have our D latch here. And our our positive is created. Well, anyways, so we have seen how it is implemented. And now we will use Questa to simulate the design. I have created my TCL, VHT, and my wave files. If you don't know what this means, you can go watch my Questa simulation video. I explained what these three files do, and so I can just call my do tb part4.tcl actual static. Let's look at if we have any errors here. We can continue. I have found why it didn't work. So in port map, you can have not like this. You can have not clock. You have to create a signal that's outside of the port map and assign the node here, create a new signal, and then this new signal can be put it into the port map. So I fixed it, now it works, and we can look at Questa simulation. Here we have our clock, the input, and then the three outputs for latch, positive triggered DFF and negative triggered DFF. The clock just pulses to 1 and 0. The input changes randomly. And then we have our three outputs. So those are our three outputs here, QA, QB, and QC for positive triggered DFF, negative edge triggered DFF, and gated D-latch. So our gated D-latch, let's look at it. When it goes to 1, so the clock in this case basically works as enable. So when it goes to 1, the D-latch is enabled and it changes with the Q, with the D. The Q changes with D input. So you can see it copies the D. And here when clock goes down to 0, it doesn't change. And it again changes when the clock goes to 1 here. So this one works correctly. Then we can look at positive DFF. Here it's undefined because the D-latch doesn't have any value. And it only changes when there is a rising edge here, which is correct because positive DFF only changes on rising edge. It goes to 1, and here we have falling edge, but we see it doesn't change, and it again changes here on the rising edge. And finally, negative DFF, it's in no state here, undefined, and here on the falling edge, it changes to 0. And doesn't change on rising edge, and again changes on the falling edge here. So we have successfully implemented positive triggered DFF and negative triggered DFF, negative edge triggered DFF, and we have simulated them so we know they work correctly. That's all for part 4, and next time we will look at part 5. So if you want to watch next part, don't forget to subscribe. And I'll see you in the next one. Bye.